Okay, in a previous lecture we have seen the air standard cycles, that is Otto cycle, diesel cycle, oil cycle and Carnot cycle. Okay, and also we have seen the difference between Otto cycle, Carnot cycle, Otto cycle, diesel cycle and oil cycle, when there is a peak pressure and when there is a maximum compression ratio. Okay, so that also we have seen in the previous lecture. Now today we have to see what is the BRAYTON cycle. After that we will see the fuel air cycle analysis. Okay, so let us see what is this BRAYTON cycle. So this is the BRAYTON cycle here. So this is the actually open cycle. In open cycle, in open gas turbine, we use the BRAYTON cycle for analysis purpose. So here what is happening here in this open cycle? Okay, so fresh air is coming from the atmosphere, which is entering into the compressor. Okay. And from this compressor, it gets compressed at high air pressure, and from that it is entered into the combustion chamber, and here the combustion takes place. Okay, here fuel is entering into this particular process. Okay, and combustion, after combustion, the whatever exhaust gases are generated that are supplied on this particular turbine, and this turbine get rotated, and here we get the work output, and these exhaust gases are coming out of the turbine. Okay, so this is the simple open gas turbine. Now here if you see on the PV diagram, there are again four processes. So process 1 to 2, that is heat is added into the air is compressed in the compressor at isentropic compression process. In 2 to 3 process, that is heat is added into the combustion chamber, that is at constant pressure. Okay, at constant pressure, and again the expansion takes place, isentropic expansion takes place. The turbine is 2 to 4, and gases which are coming out of this particular turbine, that is for 1, and heat is rejected to the surrounding. Okay, and this is the TS diagram. Okay, temperature entropy diagram. So here 1 to 2 is the isentropic process, and 3 to 4 is isentropic process. Entropy remains constant during these two processes. Okay, so next. So the BRAYTON cycle is a thermodynamic cycle named after George Bailey Brayton, that describes the workings of a constant pressure heat engine. The original BRAYTON engines used a piston compressor and a piston expander, but more modern gas turbine engines and air-breathing jet engines also follow the BRAYTON cycle. Okay, so if you see actually whatever we have seen in the previous, that is Otto cycle, or we can say that the diesel cycle. So in the diesel cycle, here there is the same, that is a constant pressure heat addition process, but here that is 4 to 1 is at constant pressure. So therefore here in BRAYTON cycle there are actually two constant pressure processes and two isentropic processes. And what was in the diesel cycle? In diesel cycle there was one constant pressure cycle and one constant volume cycle. So that is the difference between these two cycles. Okay, so just 1 second. Now here you can calculate the efficiency of this particular BRAYTON cycle with the help of this. Okay. With the help of this formula, 1 minus T1 upon T2. So T1 is the minimum temperature and T2 is the maximum temperature. Minimum temperature and maximum temperature. That is 1 minus T1 upon P2 raised to K minus 1 upon K. Okay. Now, what are the, let us see again in detail what about the in air standard cycle what we have assumed here. So if you see here in this case, air standard cycles had simplified approximations, and therefore performance estimate of the engine is better than the actual performance. Okay, so if in examination question is asked why there is a deviation between efficiencies of the actual cycle analysis and the air standard cycle analysis, then we have to say that because in air standard cycle had simplified assumptions, approximations, and therefore the performance is greater. With a compression ratio of 7:1, the actual indicated thermal efficiency of the SI engine is of order 30%, while the ideal or the air standard efficiency is about 55%. Look at this. So approximately half percent, okay, half percentage, we can say that efficiency is decreased or it is less in the actual cycle analysis than air standard cycle analysis due to these approximations. Okay, this divergence is due to partially due to non-instantaneous burning, incomplete combustion, valve operation, etc. However, the main reason lies with the oversimplified simplification of using values of properties of the working fluid. Okay, so that is the main reason. So if the question is asked in the examination, the deviation between your actual cycle analysis and the air standard cycle analysis, you have to explain the assumptions made in this air standard cycle analysis, and we have to mention these particular differences. Okay, remember this point. This is very important point. Next, now let us consider the second cycle, that is fuel air cycle analysis. So if you consider in the fuel air cycle analysis, so previously it was just a air standard cycle analysis, and now here we are talking about the fuel air cycle analysis. So here we are introducing the fuel. Okay, so we have to consider the properties of fuel also. Okay, that is the difference here. Now also, so in fuel air cycle considerations, if you see the actual composition of a cylinder, actual composition of the cylinder gas is what? Fuel plus air plus water vapor in air plus residual gases. So this is the actual composition which will be available in the cylinder. Fuel air ratio change during operation, and hence changes in amount of CO2, water vapor, etc. takes place. Specific heat changes with the temperature except for monoatomic gases, and hence the ratio of specific heats also changes. But in air standard cycle analysis, we have assumed that it is constant. But here actually we are saying that the specific heat also changes. So changes in number of molecules in cylinder with the change in pressure and temperature. So that is also one of the reason here. Next assumption, there is no chemical change in either fuel or air prior to combustion. Okay, so here also we are assuming that there is no chemical change in the fuel, okay, fuel or air prior to the combustion. So there is no heat transfer between the gases and the cylinder walls in any process. Okay, that is adiabatic. Compression and expansion processes are frictionless. Okay, this is also again the assumption, and the velocities are negligibly very small. Okay. Okay, so the velocities are negligibly small here. Okay. Now, next, so here if you see the air standard analysis allows how the efficiency is improved by raising the compression ratio of the air. If you see in the air standard cycle analysis or in the Carnot cycle, we have seen that efficiency can be improved with the help of compression ratio. If the compression ratio increases, we will get the higher efficiency. It does not give any idea. It does not give any idea on the effect of fuel air ratio on the thermal efficiency. Okay, that is these are the drawbacks that air standard cycle analysis have. So fuel air cycles in this allows study of fuel air ratio on thermal efficiency. Also, it allows study of maximum pressure and maximum temperature as fuel air ratio is varied. This helps in structural design of the engine, and this gives a good estimate of the power expected from an actual engine. Okay, this is also one of the main point that we will discuss in the fuel air cycle analysis. Now let us see, this is very important point that will be asked in the examination, that is variation of the specific heat with temperature, but that we have not discussed in the air standard cycle analysis. Okay, so except monoatomic gases, all other gases show an increase in specific heats at high temperature. This increase does not obey any law. Okay, if you see here in this particular diagram, you can see easily at the temperature, we can say that the molar heat capacity, that is Cp, here increasing with the temperature. But actually there is no specific law for this. There is no specific relation between the temperature and the specific heat. Okay. But for the understanding, we can say that here, look at this in this particular right hand side slide. You can see here Cp is equal to 1.005 kilojoule per kg Kelvin at a 300 Kelvin. Okay, for the air, Cp is equal to 1.343 kilojoule per kg Kelvin at 2000 Kelvin. So if you see here, as the temperature increases, Cp also here varies. Okay, and what about the Cv? That is constant volume. Okay, specific heat 0.718 kilojoule per kg Kelvin at 300 Kelvin. And Cv is equal to 1.055 kilojoule per kg Kelvin at 2000 Kelvin. So here both Cp and Cv are varying according to the temperature. Okay, this relation you have to remember, these values you have to remember. Now increase of specific heat is that as temperature is raised, larger and larger fractions of heat input go to produce the motion of atoms within the molecules. Okay. Now explanation regarding that particular law. As temperature is an indication of motion of molecules as a whole, therefore the energy that goes into the motion of atom does not contribute to temperature rise. And this is the reason why more heat is required to raise the temperature of unit mass by 1 degree, and this heat by definition is the specific heat. So as Cp minus Cv is equal to constant and K is equal to Cp upon Cv decreases with increase of the temperature, and therefore variation of specific heats leads the final temperature and pressure to lower values as compared to the constant specific heats. Okay, so what is happening due to this particular specific heat variation? If you see here in this case, look at this. This is very important point. As the specific heat is varying, okay, with the temperature, what is happening here? Whatever final temperature and pressure that we will get, that will be definitely reduced values. And what is the effect of this reduced value? You can see here in this diagram. So this dotted line, if you see here 1.1, 0.2, 0.3 and 0.4, that is 1, 2, 3, 4. This is with constant specific heats. Okay, and 1, 2 dash, 3 dash and 4 dash. This is the cycle with constant specific heat from point 3. Okay, from point 3, and 1, 2 dash, 3 dash, 4 dash. This is with variable specific heat. And if you see in this particular 1, 2 dash, 3 dash, you will get here very lower temperature. Okay, maximum temperature, sorry, maximum pressure, whatever we will get when we consider the variation in the specific heat, that is definitely lower as compared to actual ideal cycle, in which we assume that specific heat is constant. Okay, so here 2 dash is lower than 2 due to variable specific heats, 3 dash is lower than 3, temperature rise due given heat release decreases as Cp increases, and also 2 dash is lower than 2. 3 dash to 4 dash, 4 double dash. If you see here, this is 4 double dash. So resulting adiabatic expansion 3 dash to 4 dash, correct expansion, specific heat decreases as temperature decreases during expansion. Okay. Now let us discuss about the dissociation loss. Okay. So this is again the very much important factor that we have to discuss in the fuel air cycle analysis. Okay. So I think we will discuss this particular dissociation loss in the next lecture. Okay. Thank you very much.